the can. Okay, so I have here some regular thread. Now, thread and rope are really interesting and useful things. They can hold up really well under tension. A tiny little thread can hold up a significant amount of weight. So of course, this thread can't hold any weight on top of it. That's because the compressive force that it can take is basically zero. It immediately buckles under any compression. So I'm going to be trying to make a table that's supported by just thread. So first, let me just try to support these two triangles of cardboard using just thread as the legs. And as you'd expect, it buckles immediately as soon as I put any pressure on it. Well, maybe things aren't balanced just right. Let's try to put some center weights on it and try to balance it a little better. It still doesn't work. So you can see that I've secured these two pieces together with string, and they hang here just fine. But watch what happens when I set it down. It doesn't collapse. Somehow the strings are able to support it still. Look at this thing. So cool. Okay, let's see how much weight it can actually support. The can. Here's some scissors on it. Whoa. So to figure out how this is working, let's add a little bit more weight and see where we can see some of the deformation. Oh, so where did it break? The center string. So without the center string, we're out of luck. But these three outer strings still played a role. If you only had the center string, it would just tip over. These kept it balanced. So basically, whenever one side started to get pulled, it pulled these in tension to stop it from tipping. So what's cool about a contraption like this is because it only relies on tensile forces and not compressive forces, you could build it out of materials that have a very high tensile force, like spider silk. And if I did that, I would only need a thread that's 147 microns in diameter to support this entire 5-pound weight. If I made it out of carbon nanotubes, then I could get it to support this 5-pound weight with this thread in the center that is only 22 microns in diameter. Now, this type of structure is called a tensegrity structure and relies on the tensile strength of the cords within it. It also relies on the compressive strength of the beams, but usually these compressed beams aren't touching each other. For example, in this one, these were under compression. You could notice that this one was slightly bending when we put weight on it. So it was under compression in parts of it, but they're not usually touching each other, so it appears to be floating. Now, tensegrity structures are really interesting because it gives the illusion of floating. You can actually make real structures based on these principles here. For example, the largest tensegrity bridge was opened on October 2009 in Brisbane, Australia. It's called the Kurilpa Bridge. You can see it here. Now, what's cool about the tensegrity structures is if you viewed it from the outside as a black box, you wouldn't actually know it was only under tension in the threads there. It would seem like its own component where you could kind of push on it and it was kind of squishy, you could turn it and it was squishy, but you wouldn't know that it was actually just supported by threads. Now, I tried to look up when the original tensegrity system was created, and there was a lot of controversy about it, but then I realized the original tensegrity system is our own body. Basically, our tendons are like the cords here, and our bones are like these discontinuous members under compression. So our tendons are only strong under tensile strength. So you can only pull on them to have them be strong, but you can't push on them. So when you actually have to lift a weight or pick something up, it does it through tensile forces, and the compressive forces are only in your bones. And so it appears like your tendons are doing all the work here, being pulled up by your muscles, but your bones are actually under compression. So in your musculoskeletal system, your tendons act like the members under tension, and your bones act like the discontinuous members under compression. So it's really neat that our bodies have this tensegrity structure, meaning that if I want to pick something up, it doesn't require my bone to be shaped like this in order to take the compressive forces, but basically all I need is these discontinuous members like bones that are held together by these tensile forces of my ligaments. And so that makes me be able to move in different directions and be very pliable and bendable, but still really structurally sound. And thanks for watching, and I'll see you next time.